So maybe we'll resume. So maybe I was not very clear about some points, so let me try to emphasize some of these points. Typically, the difference between the Bayesian framework and the framework I'm considering here now is that the IID framework is that in the Gaussian framework, you usually assume that you have some prior on this prior defines how likely is it that each function, each possible target function will appear. And usually, I mean, one way is to have a Gaussian process. And this Gaussian process will generate some functions, f, and then you assume that the data comes like, for example, the instances x are generated uniformly, for example, or with some distribution that you define. And then the labels are determined by applying this function to the instance and adding some noise. So usually in the Bayesian framework, you define both the Gaussian process that defines this function, some noise function here, some distribution for the x's, and that's your prior. And then for each realization of this prior, you have a corresponding function, right? Labeling function. And this labeling function defines now how the data is generated really. So you have two steps. One is to get this f from the Gaussian process, and the second one is to get the data and label it according to that function f. In the IID case, you directly assume that there is one fixed distribution that generates the x and the y's. So it's like considering one. Maybe it's too close. Okay, so maybe I should. Yeah. So okay. Yeah. So basically, in the IID framework, let me take this. In the IID framework, you have just one way to generate your data. In the Bayesian framework, you have many different ways, so many different PIID distributions, and each of them is associated with a certain probability. So there is a certain probability that this function f would be chosen, or that this distribution would be chosen, if you will, and you take like the error under the expected, so expectation over this prior. Sorry? Oh, what is the likelihood in my terminology? The likelihood would be, well, I mean, the likelihood usually is the probability of observing the data given some hypothesis, which here, the hypothesis would be this function f, and this would be just defined by this probability. So it would be, if in the case you have, say, for a Gaussian noise, it would be the product over the instances of the probability of, maybe this way is better, you see? Probability of xi, yi, given this function f. So that would be the product of, say, some normalization factor, e to the minus f of xi minus yi squared, say, dividing by 2 sigma squared, right? So basically, this means that we assume that there is a Gaussian noise that corrupts the labels that are generated by this function f, right? And then you have some, and the probability of having this function f, the prior probability of this function f is some kind of Gaussian, say, right? So in my case, I'm not considering this anymore. I'm just looking at, in a way, I'm just looking at the likelihood itself. But the difference is that in the IID case, the likelihood is not generated by a given function with a certain noise. It's just any, and the given distribution of the instances is just any fixed distribution over the pairs xy. Okay? So there is only one problem in a way. Whereas in the Bayesian case, you have many different problems, and you take an average over all these many different problems. Okay, so within this context, the important question is whether let's see. So we have these instances that come, right? Xi, yi, that are generated by this unknown probability. We observe n of them, and then we create a function, gn, that to each x associates a y. And hopefully, this y that we associate with the x is one that is the right one, in a way. And the right one means that if we look at the expected value under this distribution PIID of the error, so the difference between, so let's say the indicator that gn of x is not equal to y, we take the expected value under this distribution of the pairs xy, we want this to be small. Okay, and that's our expected loss. Now, if we look at the expected loss, so let's say L of Gn, Gn being the model that we have constructed after seeing these n pairs, we would like this to, say, converge to the best possible error, which is L of G star. So this is the best possible error we can reach. So the function G star is the function that minimizes this expected error, right? So that's what is called usually the Bayes classifier. It's kind of confusing because Bayes here is used in a completely different meaning than before. But let's say this is, basically the classifier that tells you the right thing. This error is not always 0. I mean, it can be 0 if for each given x there is a unique valid label. But maybe for a given x there can be several different labels because there are some errors in the measurements or things like that. So when there is some error in the measurements, this cannot be 0, but it can be close to 0, let's say. So in general, it's not necessarily 0. And ideally, we want our algorithm to be as good as the best one, right? And this convergence here usually is studied in the context of increasing sample size. So ideally, as we get more and more data, more and more observations, we would like our error to converge to the best error. And this notion here, when this convergence occurs, we say that our algorithm is consistent. Because ultimately, with enough data, we will have identified the best model in a way, or the right model. So we would have learned the problem, basically. So the question is whether this is possible and under which condition this will occur, this consistency will occur. Right? There is this notion of universally consistent algorithm. So universally consistent algorithm is one algorithm that no matter what is the underlying distribution here, will have this property that ultimately, with enough data, it will do the right thing. The question is whether this is possible at all. Can we always learn, no matter what the data, how the data is generated? And it turns out that it's possible, and it's quite easy actually. So, I mean, is all this clear, or are there any questions? Yes. Oh, so the question is, what do I mean by x generated uniformly here? Sorry. Here. So, I mean, okay, this is just an example of one possible way to generate the instances x. Uniformly here, I meant, say, you consider a cube in a d-dimensional space, you put a uniform distribution, and you say, well, the probability of sampling each x from this cube is uniform. So that's one possible way. Because basically, I have to assume that my data comes from somewhere. So I can say, well, I don't know, maybe our data is some measurements about people, like, you know, the height and the weight and, I don't know, the blood pressure and so on. So the height is between 0 and maybe 2 meters, and the blood pressure is between, you know, something and something, and so on. And basically, I will define some kind of cube, and I might assume that any possible value in this cube is equally likely. Let's say if I don't know anything about how people are distributed, then I can say, well, just assume that this is uniform. Or I can have you know, more knowledge, and I say, well, people are more distributed like this on the height scale, and maybe on the blood pressure scale is like this. So I will define some kind of multidimensional distribution here, and I will say, okay, let's assume that this is the right distribution for my instances, and then the function might be, this function here might be, I don't know, the risk of cancer, let's say, of these people, and this risk will be some measure between 0 and 1, let's say, and I assume that there is a function that, given the data of these people, given all these measurements, tells me what is the risk of cancer, but I assume that in addition to that, there is some corruption in these measurements that I cannot be sure that this is exactly the risk because I don't have all the parameters. I'm only observing some values from these people. These values may have some noise and so on. So I will kind of define some noise distribution. Is it clear? Kind of? Yeah. I mean, the point here is, okay, that's one way of doing things. In my case, I don't want to force me to define things in a certain way. I'm just saying, okay, let's assume there is a distribution. I'm not telling you what this distribution is. And what I will try to do is, no matter what this distribution is, try to come up with an algorithm that does the right thing in the sense that it converges to the best possible error, which means that for any given x, it will give you the label that is the most likely for this x. Right? So within this distribution, the most likely label for a given x. So if we are looking at some specific instance, small x, what we want is to find the label y that maximizes this probability, right? More or less. We want to find the label that is most likely given a certain instance. And when we find this label, then we are at the best predictor. So the best predictor is the one that always assigns to any x the most likely label. Well, at least in this case where we have this kind of error, the misclassification error in the binary case. Yes?
I suppose G star is not a function of the observation data.
It is. So, oh, sorry, no. Yeah, G star is not a function of the data that we have observed, these n instances. No. It's something that is absolute.
Can you do something with the best possible thing you can do with the data? Can you balance the difference between your algorithm and the best possible thing you can do with the data?
Yes, you can do that in the online setting. And when you restrict yourself to a certain class of predictors, you can say, okay, because in the online setting, you only see your instances, but you don't see them all at once, right? So you see x1, y1. I mean, this will be clear once you see the Nicolo's lecture. You see x1, you see x1, you have to predict y1, and then you see the actual value that you should have predicted, and you see the next instance, you have to predict the y. Once you have predicted it, you see it, and so on, until xn, yn. So this is all you see. You never get to see anything else, right? There is no notion of other underlying distribution or anything like this. So within that framework, you can look at the errors that you made every time you make a prediction, the cumulative error, and you can compare this error to the error that someone would have made knowing this data or seeing this data. So you have some other, so let's say your algorithm is called Gn, so for each different n it has a prediction. and you have some G0, which is the reference predictor. This G0 for x1 predicts something, for x2 predicts something, and so on. So overall, it has a certain error, and you can compare your error on this sequence, on this specific sequence. You can compare the error of the algorithm to the error of this reference classifier, and then say how good you are with respect to this one, and then you can take the best one within a certain class. Let's say you look at all linear predictors, and you take G0 to be the best linear predictor for that specific sequence. So in this context, you can make statements about a specific sequence. Yes? Here?
So is there no notion of universal, the best thing you can do about that's what it's about?
Well, no, actually. Yeah, so the question was, is there a universal notion of the best thing you can do with a certain set of data? And actually, apart from this special case and setting things in this way, in the more general kind of batch learning framework where you have data and then you want to make predictions, then you have to assume something about the data that you will see next, right? To make any statement. So the best thing you can do once you have seen this data depends on what will come next. And what will come next in our IID case is defined by this distribution. So the relationship in the IID case between what you have observed and what you will see later on is that these two things come from the same distribution, which you don't know, but they come from the same distribution. So you can think of this data that you observe as telling you something, giving you some partial information about the distribution of the data, and you hope that this distribution of the data will be the same next time you'll see instances. And you're trying to do your best guessing what is this distribution. Okay? Question?
Well, oftentimes when you do this kind of learning, you have to cover some regularization that they want
Yes.
to minimize the significant amount of time to look at. Yet you said that you're throwing away any prior notion you have about the function of the mechanism. But when you do regularization, that's sort of what you're doing.
Yes, okay, that's a very good question. So the question is, usually when you do learning, you do have some notion of regularization or prior knowledge. And what I said here is that I don't use the prior knowledge. Okay, so the point here is I don't want to make statements that depend on this prior information, right? So I want to prove results independent on what I know about the problem. But still, my algorithm here might very well use some prior information. But I just don't want to prove something under the condition that this is true. So my algorithm might use some regularity, some regularization, and so on. But I don't want to say or to assume that this is the right notion, let's say. Maybe it will become clearer once we get into this consistency thing, hopefully. So the question is, how do we get a consistent algorithm? So an algorithm that can learn anything, right? So that ultimately will converge to the best thing. When your instance space, your X space, is countable, it turns out to be very easy, even trivial. What you do is, countable means that you have some kind of discrete thing, like you can count all your instances. So basically, you have an instance x1, x2, and so on. You have possibly infinitely many of them, but you can count them, right? So in this case, I mean, this is not a good case because, you could simulate the case of human patients with a countable instance space. You just have to say, let's assume that we measure the height within 1 centimeter. So every measurement here would be an integer number of centimeters. Maybe the blood pressure is within, 1%, let's say. So we discretize this axis as well. So if all axes are discretized, then we have even a finite space of possible people, right? Instead of discretizing within a fixed radius, we can even say, let's assume that the numbers are rational, let's say, right? The number defining the size and the blood pressure are rational. still we would have a countable number of possible patients, right? And if we have that, then it's easy, because what we do is that for each patient, for each point in the space, we look at how many times the label was was 1 and how many times the label was 0. So I'm kind of, switching in between the case where the label is a real value and the case where the label is binary, but it should not really matter. So let's assume it's binary. So maybe the label here means the patient has cancer or doesn't have cancer, or has some kind of disease or doesn't have some kind of disease. And I'm looking whenever I have these kind of measurements, so a patient having size equals something, blood pressure equals something, and some other measurements, Z equals something. So whenever I observe the patient having that, I have either Y equals 1 or Y equals 0. And I just, wait until I observe a lot of patients. So if I observe a lot of them, then eventually I will have observed a lot of them that have exactly these measurements. For these ones, I say, well, maybe 10 times I had this, and 100 times I had 0. So I can have kind of an accurate evaluation of how likely it is that a patient having these measurements will have or not have the disease. Yes? Yes, yes. So, yes. And the point is that this, so when it's finite, it's clear, right? When it's finite, with enough observation, we will have observed many times each individual case, and we can make accurate predictions because we just say, well, we observed, this fraction and this fraction, so we make the prediction, and this will be accurate, and this will obviously converge to the right thing, and we will have consistency no matter what the distribution is. In the countable case, it's like, so I forgot to repeat the question. The question was, in the countable case, you might have, a long tail of things that you still haven't observed at any given point in time. That's exactly the point. But the thing is that, let's say, if you look at, if you order your instances by decreasing probability, so let's say x1 is the most likely one, x2 is slightly less likely, and so on. So you have some probability which is like this, right? So when you take a sample of instances, then probably you would have x1 included because it's the most likely, maybe not x2, but x3, and so on. And so most likely you would have observed, after some time, you would have observed kind of the first part of this distribution, the most likely ones. But then there will be a tail of instances that you still haven't observed. But the point is that the total probability of the things that you have observed will be large, right? So if you were to compute the expected value of your error, this expected value would be dominated by the instances that are most likely. So if you take new examples, most likely they would also come from the same head of the distribution. So just because of this, you would have enough observation after some time so that even though you haven't still observed some data, this data that you have observed is dominating the expected error computation. So because we are looking at the expected error, after some time we will have the right thing. So the tail will become smaller and smaller in a way. Okay, so here we have not gained anything. We are saying that if we assume that all data spaces are countable, which is the case when you're using a computer, right? There is no way to define anything beyond finite even in a computer. But even if you were to have a infinite computer with countable number of states, still you would be able to do learning in this sense of consistency very easily. Oh, sorry, should have turned this off. Okay. Now let's look at the uncountable case, which is somehow more interesting. Well, in the uncountable case, so where the variables, for example, are real numbers, you don't have this phenomenon that you have a discrete set of instances that you keep observing again and again, right? Any instance can be different from one another. So if you look at the observed set of instances, they have measure 0. So which means that, at least if your probability is continuous, which means that new examples will never be exactly the same as previous ones. So you can't make this trick of just observing what happens and counting how many times you have 1 and 0. So this trick doesn't work. But you can still do something which would work in any case, which is taking a local majority. So basically, at each given point, you observe what happens in a small neighborhood around this point. Right? For every point, you define a small neighborhood, and you look at what happens, and you count how many times you have positive and negative patients, and you use that as a prediction. Like you take the majority over this count as a prediction. And the conditions for consistency to occur are that this neighborhood should become smaller and smaller, right? As you have more data, it seems intuitively fine correct to have a smaller neighborhood because you have a more dense coverage of your space. But at the same time, you should average many points in that neighborhood, because the larger the number of points you average, the more accurate your prediction of the probability will be. Right? That's kind of the large number theorem. An example is the following. If you take what are called histograms in RD, so that's this case, right? You have RD, or at least a bounded subset of RD. Let's say, so it's more 0, 1 to the power D, let's say. And within that set, you define cells that are cubic, right? So you just take a grid in all directions, and you define these cells. And what you do is that you take the average, as I said, over the cell of the counts of positive and negative labels, and you arrange so that the size of the cell Hn, which is the grid size, you make it so that as n increases, this size goes to 0, as I said before, but does not go to 0 too fast, so that you ensure that Hn to the power d, that's the volume of the cell. So this volume multiplied by n should go to infinity, which means that the expected number of points that will be in any given cell is the volume. Is n times the volume after you have observed n points. The expected number of points that you have in the cell is n times Hn to the d, right? So this expected number of points that are in a cell should go to infinity, so that you have this increase of number of points that you average. Okay? And to prove that this is the case, that this kind of algorithm is consistent, you just use the fact that continuous functions with bounded support, so you have to assume this bounded supporting boundedness. They are dense in any LP space. And so, essentially you want to prove some kind of convergence of two functions, right? This convergence will happen whenever you have convergence in LP, which is kind of the natural space to define functions when you have a probability measure on your space. Because they are continuous and on a bounded domain, they are uniformly continuous, which means that any such function can be approximated arbitrarily well with histograms. Histogram being like piecewise constant function, right? So something like this. So any function which is continuous on a bounded domain can be approximated arbitrarily well by some function like this. So by just decreasing the size, making more steps, ultimately that would converge. And this convergence is provided by the fact that Hn goes to 0. But then on each cell, you want convergence of these counts towards the true probability. Let's say this is the true probability of being ill given a certain measurement value. So to get this convergence, you just need this. So this will guarantee that the values of these steps will converge to the right value, and the other condition will guarantee that the step size go to 0, so you have approximation. Yes?
Like sort of educational that's already
Yes. Yes. Yeah, so the question is whether this is related to the sampling theorem in information theory. Yes, you can think of it this way, although it's kind of simpler because, yeah, I mean, that's intuitively connected, but it's not really, I mean, it's not the same mathematics, but it's intuitively connected, yeah, sure. But, okay, the point was to show you that, you know, if you want a perfect algorithm, perfect in the sense of being able to learn anything, right? It's easy. In the countable case, it's trivial. In the non-countable case, it's not hard. So why bother, right? Yes? Yeah, the question is how innocent is this assumption that we are considering measurable functions? Yeah, that's the point, right? It's kind of connected to the fact that you are introducing a probability distribution for the data. If you introduce a probability distribution, then the best, I mean, and this probability distribution satisfies the regular actions for a probability defined on a continuous space, then this best function will be measurable. So you can restrict to measurable functions. But this means that you have hidden the subtlety in the fact that you assume a probability distribution generating your data. So in a way, just this fact that we write that there exists some distribution generating the data already restricts considerably what we are looking at or considering. And it's not innocent in a way because it has a lot of implications. But you know, it's the framework that we have chosen to work with. But yeah, I agree. It's I mean, we'll see maybe in a bit more. Yeah, maybe it will be clearer. But yeah, I mean, it's definitely not innocent. That's the point. Although it seems so natural, right? Okay, so basically you can learn anything. So did we solve the problem already with this simple algorithm, this histogram-based thing? Well, no, because now, given that there are consistent algorithms, the question is which one is the best, right? Is there one that goes faster to the best function, or that goes in certain better way? So again, we are in the classification case. And the same kind of thing occurs for regression or other settings like density estimation. So we can restrict to classification, and that would be fine. So the problem is there is this notion of no free lunch, which means that, unfortunately, there is no way to tell apart two algorithms by looking at how they converge to the best. So here's the first definition of this no free lunch algorithm theorem. Sorry. So that's the most cited version and the most classical one, although it's not the most interesting one. But okay, let's start with this one. So you look at what is called the out-of-sample error, so which is the probability that you make a mistake on samples that are not in your training data. So X is that you have not observed so far. We have seen that, you know, on examples that you have already observed, it's easy, just count how many, you take a majority vote, and that's easy. So this is saying, okay, let's not worry about the examples that we have observed. Let's look at those that we have not observed yet. Then what you do is you can consider, and this is kind of Bayesian in spirit, you consider some kind of uniform probability distribution. I mean, it's not easy to define. You have to assume a lot of restriction, but let's keep the intuitive interpretation here. We consider a uniform probability distribution over problems. So which means that we assume that any possible thing can happen uniformly. Any possible distribution is equally likely, or any possible data generation is equally likely. Hard to define, but let's assume we can do it. So under this uniform distribution, then of course, at a given instance, the expected value under this distribution that the label would be 1 will be the same as the expected value that the label would be 0, right? Because both things can be equally likely. So if we have this, then for any possible algorithm, the expected under this uniform distribution of the loss, the out-of-sample loss of my algorithm would be half. I mean, it's kind of easy to see because it just says that on this new data that you have not seen so far, the label can either be 0 or 1, and there's this distribution over problems, so the loss is a half, right? No matter what the algorithm predicts. So how do we interpret that? So basically it says that on average over all problems, any algorithm has the same loss, which is kind of disturbing. Right? Another way to state it is like over all possible data generation mechanisms, our algorithms have the same error when measured on future instances. Which implies that if you have one algorithm that is better than another on a certain given problem, then it will be worse on another problem. So you cannot ever say my algorithm is better. You have to say my algorithm is better for this specific problem because it will be worse for some other problem, right? So basically, if you want to make any meaningful statement, the implication of this theorem is that you have to restrict the set of considered problems. You cannot say that an algorithm is good without specifying good for what. Okay, so does this kill all hope? Well, actually, this kills all hope, and even worse, there are even stronger statements that we can make. I mean, apart if we make choices and express preferences about the kind of data generation or the probability distribution that we expect to see, right? And this means we need to choose a prior, basically. So that comes back to this question about regularization. Algorithms, if you want to do a good job at a certain class of problem, you have to choose a prior that corresponds to that class of problem. Okay. So, I mean, there are several ways in which we can criticize this statement that I just explained. Which, I mean, the first thing is that it's not really realistic to kind of define uniform distribution over classes of problem because what is a class of problem? Is it all possible distribution? If it is, then you can't really define a uniform distribution on a countable set of things. So mathematically, it's hard to define apart if you restrict yourself to the very specific finite case. And also another criticism is that, another thing is that we are considering the off-sample error, so the error measured on new instances. And before, I was saying that we are considering the expected error, which is the same thing, but including the instances that we have seen. So you can say, well, maybe this is not the same. It is not the same, but they differ by a small fraction, especially so when the sample size increases, you can show that basically the off-sample error, so the error measured on what you have not seen, is the same as the error measured on everything, things that you have not seen and things that you have seen. There is a small difference. And in the continuous case, they are actually the same because you never really re-observe the one thing that you have observed. Okay. So the point is that there are always cases where algorithms can be beaten, and you can actually make a stronger statement within that. Now that this IID framework for a given fixed probability and for the normal error, the expected error, what you can prove is that sequence of classification rules DN mean an algorithm that for any sample size gives you some model, right? So you can think of this as an algorithm. So for any algorithm, there is a universally consistent algorithm. There is another universally consistent algorithm, which has a lower error for some distribution. That's important. For a given problem, you can come up with a problem for which this new algorithm will perform better. So that's another way of saying that there is no better algorithm, because if you give me an algorithm, I can construct another one, and I can construct a problem on which this other one algorithm does better. Right? Okay, this is more or less the same consequence. Now, there is a variation to that, which is you can also show that if you give me an algorithm, I can construct a problem for which your algorithm, even if it's consistent, so even if it ultimately will converge to the best error, and even if this best error is 0, so even if ultimately with enough data, your algorithm, the error of your algorithm will converge to 0, I can construct a distribution for which, for a given sample size, the error of your algorithm will be arbitrarily close to a half. So even if your algorithm ultimately will be good and perfect, on a finite sample size, it can be arbitrarily bad. So you have absolutely no guarantee on, on this finite set of data. So I mean, after observing this amount of data, it can just be, it can just have an error which is arbitrarily close to half. That is even more disturbing. Now the point is that here, this statement is kind of, I kind of tricked you here, because what is not completely explicit is that this distribution on which this happens depends on the sample size. So for any integer n, I can construct distribution for which this is true. But in practice, the distribution doesn't change as you get more points, right? So you have to have a statement that has a fixed distribution for any n. And you can have one. And here is it. Here it is. You have this so-called slow rate phenomenon. So here is how it works. You give me a sequence of numbers that converge to 0. They can converge to 0 arbitrarily slowly, no matter how you want. They have to converge to 0 ultimately, but it can be that they are constant for a median set of values, and then a smaller constant for 10 million times, and then decrease arbitrarily slowly, but ultimately converge to 0. Now, given this sequence, I can construct a problem, a distribution, which has base risk 0, so which means for which the best error is 0, and for which, if you have given me an algorithm, right, that is even consistent, right, so that for which the error will converge to 0, the error of this algorithm will not converge faster than this sequence. So let me rephrase it. You give me an algorithm that is consistent, which means that it will learn anything, ultimately. You give me a sequence that goes very, very slowly to 0, and I can construct the distribution for which your algorithm will not be faster than this sequence. So basically, an algorithm can converge arbitrarily slowly to 0. So maybe it will just stay at a half or very close to a half for hundreds or billions of instances, and then slowly goes to 0. So again, it's the same thing as saying you don't know how close you are to 0. So basically, you can never know how close you are to 0, even if you can prove that your algorithm will go to 0. So how do we prove that? I'm getting close to the end. So maybe I just skip the proof and go to the conclusion of this lecture. I mean, we can go back to that if you want tomorrow. Okay. So let's just wrap up. Actually, I'm over time. Yeah, sorry about that. So yeah, let's just summarize. So consistency is in the countable case, just memorize everything. If you are in the continuous case, it relies on this measurability notion, which is kind of fishy and implicitly introduced by the fact that we assume a probability distribution. And these non-Freudian results rely exactly on this comment that was made before, on the fact that we never have seen enough data. So if we have a kind of countable space, you can always have a large amount of instances that you have not seen. Even though this large amount has a small probability of occurring, you can, this small probability can be your rate of convergence, and you can make it converge to 0 as slow as possible, essentially. Okay, so Yeah. Let's skip to tomorrow. Thank you. If you have any question, maybe quickly. Okay. Thanks.